Hi, I'm Bruce Palmquist, and I teach in the Physics Department and the Science and Mathematics Education Department at Central Washington University. And I'm also the Physics Department liaison for the college and the high school program. And I wanted to just spend a little bit of time talking about some different online lab experiences, whether you have to teach fully online, partially online, or you're not teaching online at all, you're teaching face-to-face. There are a lot of resources that will help you and your students learn science in a different way than doing an experiment in the classroom. We know that hands-on science is really an important way to teach science, not just cookbook labs, not just manipulating things, but manipulating ideas as well. And while using computer simulations aren't exactly manipulating things, that's not the only way to do an online lab. So I'm going to talk a little bit about some different ideas, give you some different resources as well. There's this presentation. I saved it on my Google Drive, gave it a short link, so you can go to this presentation, download it, and get access to all the links. So I'm going to be talking about some goals and some best practices. And I'm going to be focused more on physics and astronomy because those are the classes that I teach the most, and those are the ones that I have taught online. But some of the resources that I'll share are good for all science areas. And then I'll share a couple that are specific more to earth science. But first, I'm going to start off with some goals and best practices of lab teaching. Again, the first slide I'm going to show is going to focus on physics. The second one will be a little bit more general. I got it actually from an earth science teaching website. Well, I got it from another faculty member who got it from an earth science teaching website. When you have lab experiences, we think about teaching the content, maybe teaching some of the methods, but there are other skills that are important in teaching science labs as well, and that is science communication. And we know that science is a collaborative endeavor, so how can you facilitate collaboration, especially if it is in an online setting, your science experiment or your science experience? I'm going to share some general resources. They're going to show up as words on the slide, so that's why it's really important that you download the slides. If you haven't done so already, go back a little bit and look at the short link. And then I'm going to share some specific assignments that I've created for physics and astronomy classes, just to give you an idea, because it's one thing to say, well, here's a way that you can teach science online. But then I'm going to share some specifics. Not that my specific assignments are the greatest. Maybe they're not even the goodest or the okayest, but at least you can download them and say, oh, okay, this is kind of reasonable, but here's how I would improve it. This slide is going to share some goals. AAPT is the American Association of Physics Teachers, and they looked into, they had a big group that talked about, okay, physics labs, physics is a lab science. What do we want students to get out of a lab experience? And there are a few different things to look at. So one of those is constructing knowledge. It's really important for students to collect and analyze and interpret data from their own observations. So notice it says constructing knowledge. It doesn't say gathering knowledge, writing down knowledge. So it's students figuring things out for themselves with guidance, of course. So I said collecting, analyzing, and interpreting data from personal observations. That doesn't mean they're just kind of looking around, oh, what am I going to observe, right? The teacher actually sets up some phenomena for them to actually observe. Modeling. So creating models, developing and critiquing predictions that they're making about both abstract representations and maybe smaller versions of real systems. So analyzing mechanical advantage, building some different types of levers, lifting and moving some different weights, those would be models, but also computer models as well. So developing a computer model, making some predictions based on that computer model, that is also a part of science. Another thing that's important for a lab experience, and this does say physics lab experience, but none of my bullet points here are actually going to mention physics. I might talk a little bit about physics because that's what I know the most. But so far, no, constructing knowledge, that would be appropriate in other sciences as well, similarly with modeling. Designing experiments, that means a lab experience shouldn't just be following somebody else's direction. Sure, there are some experiments in physics, some lab activities in physics with electricity, for example. You want to be safe. Or in chemistry, you're not just going to mix any old chemicals together. So designing an experiment to figure out what happens when you mix bottle A with bottle B, or you touch wire A to wire B, that is not what this means. But this means that students should have some freedom to do certain things. So maybe you set up the parameters that no matter what they mix together, no matter what they touch together, they're not going to hurt themselves. So you give them a few light bulbs and a battery. That would be what you could do in the hands-on classroom. Well, they're not going to hurt themselves. The worst they might do is burn out a battery. And yeah, you don't want them burning out lots of batteries because there goes your budget, but that is not dangerous. So developing engineering troubleshooting experiments. So maybe you set up most of the experiment as the teacher, either physically or virtually, but they make maybe the last 2 or 3 decisions. Or you give them something that maybe doesn't work and they have to troubleshoot it. So designing doesn't necessarily mean designing from scratch. It could mean choosing from a few limited parameters, but it means that you, the teacher, you don't tell them exactly what to do. Developing technical skills. Yeah, that's clearly something that you think, well, got to be hands-on there. But that doesn't necessarily mean that you are manipulating physical things. So you could figure out what are some limits. So maybe you have an online voltage meter and you figure out, okay, this online voltage meter can only read a certain number of volts or a certain number of amps. How can we combine these circuit elements such that we still are within the tolerance of the meter? So determining what are some limits of the equipment is important as well. And also recognizing it. So if you have a virtual ammeter and a virtual voltmeter, the student still needs to figure out, well, where do I touch the probes to measure volts? Where do I touch the probes to measure amps? So you're not physically holding the probes, but you still have to move them to get the proper reading. Analyzing and visualizing data. So that's something that can easily be done online. There's a lot of data online. And in fact, scientists who do science as a profession, many of them don't touch the physical equipment. Maybe they haven't since they were graduate students. Now their job is to take lots and lots of data and make sense of it and communicate it. Oh, communicating science. So that's the last one, presenting the results in a clear and readable format, making sure that the results that you present actually address your hypothesis and are convincing. Pretty much all of these bullet points can be done in an online lab environment, either using simulations, using remote instrumentation, or using things that can be found around the house. Probably the most difficult one would be the 4th bullet point, developing technical and practical lab skills, but some of that can be done online as well. Like I said, with a virtual multimeter, you still have to know how to connect the virtual probes to the virtual circuit. The previous slide was from the American Association of Physics Teachers. This is from the Science Education Resource Source Center. And these best practices for teaching about the Earth, that was actually the heading of the section. But this is not just Earth science focused. You'll get ideas here that are appropriate for pretty much any field. So one thing you want to do as a teacher is develop a sense of community and help your students develop a sense of community. So that might mean facilitating student-to-student interaction, online discussions, using collaborative documents, Google Documents or OneNote class notebook for students to work together. Give students projects, assign students roles so they each can do a certain part of a project. So maybe somebody does the research, somebody uses they analyze the data, somebody else uses some online instrumentation to analyze a phenomenon, and then they combine their work together into a final project. So making the content place-based and context-rich. So use questions, use phenomenon, use situations that the students care about. So things that they might be talking about already. So if your community is one, maybe there's a ballot initiative or the county commissioners are thinking of approving a wind farm. So a wind farm, you can talk obviously about earth science-based phenomenon, wind, weather, topography, but with physics, you can talk about energy, electricity. So you could talk about all those things in an abstract sense, but if you use something that the students are going to care more about because it's something that they're familiar with, then so much better. Talking about climate change. So don't just talk about climate in the generic sense, talk about climate change, share data from different parts of the world. So maybe one place in the world has a more stable climate, another has a climate that is changing much more drastically. Have the students look at those places, data from those places, and try to figure out, well, what's different about those two, and teach climate that way. When you develop activities, you should develop activities that you can use with a lot of different size groups of students. So for example, think, pair, share, that's something that can be done with small groups of students. Think, pair, of course, implies 2 students. Jigsaw assignments, students in small groups, each group gets a certain component of the assignment. So for example, you have them read a research paper. Each of the 4 students in a group gets part of that paper, and they study their part of the paper, and then they teach the other 3 people in the group their part of the paper. Peer review. Every student in the class writes something, and then that's put out, and 2 or 3 classmates will review what that student does. You could also have sort of whole class assignments where there's brainstorming. You've got a bulletin board, and every student in the class has to put 2 ideas on that bulletin board, and then each student in the class has to look at the bulletin board and decide which of those ideas they think are the best, however you want to operationally define best. Don't just teach the content, but include information literacy. So teach students about citations. You look something up online, and the first link you get, that isn't necessarily the best one. So what is it about a source that makes it a good source? And you can also build in assessments that facilitate this or that enable students to practice this. So they might need to, you might give them 2 articles and obliterate the title of the article, the author of the article, and where that author works, if they do work, and then have the students critique each of those articles. Which one do they think is the quote-unquote science article? Which one is a pseudoscience article? And no matter what you're teaching, using effective management and assessment strategies. So a variety of assessment types. Use rubrics that the students can access to begin with. Maybe even have the students help create the rubrics, or at least some component of them. Make sure that you've got good, clear expectations. Again, the title of this is Practices for Teaching About the Earth, but it is all these bullet points are appropriate for other topics as well. And I call these soft skills. I'm not sure if that's the best label, but the two skills I have here are collaboration and communication. There are a lot of tools to facilitate collaboration. And again, if you access the PowerPoint, which there's the link to at the very beginning, you can click all these hot links here. So the first three, Microsoft Teams, OneNote, Class Notebook, and Google Tools. I've used Class Notebook and Google Tools, but the links there, I mean, you could obviously go online and just search Microsoft Teams and you'll get a bunch of different references. But those three are from a podcast that I like called Cult of Pedagogy. And it's a team of teachers that put this together. So those links aren't just the links from Microsoft or Google. They take you to a podcast by a teacher who gives you some of her perspective about each of these tools. On campus, we use Canvas as a learning management system. Some of you at the high school level might use this. A lot of you use Google Classroom, pretty much the same thing. Built into Canvas are online discussions. There are other online discussion tools as well. And then for communication, you might think, well, written lab reports, and obviously those are sort of the traditional way. Those can be done individually. They can also be done collaboratively with each person in a group writing part of a report. Students could just write a lab report outline, so maybe just sort of a skeletal lab report. They can make a poster, and there are a lot of ways to share posters online. A poster could be a Google slide, and those could be put into Google Classroom or whatever your learning management system is. A podcast, I like having students develop podcasts, so they could make a podcast about their science activity, and one person could be the interviewer and the other two people could play the role of the scientists that did the actual experiment or lab activity. Students could do a video summary, and a really good tool for that is Flipgrid. And one of the reasons it's a good tool, it's browser-based, it's fairly ubiquitous. It's part of the Microsoft suite now. But it's time limited. There's an easy way for you, the teacher, to make comments that are that can only be seen by the students who created it. But there's another video aspect of it where students can react. So you could do video peer reactions to other people's experiments. And I'm actually going to show you a couple of these links here before I go on. So this will be a little bit clunky. Sorry about that. So that's me again. And actually, I should have kept this live. That's one thing I'm going to show you in a little bit. So this is just the podcast. This one is the one about Microsoft Teams, just so you see what this looks like. So this is the article that actually goes along with it. There's some embedded videos, and you can also link to podcasts related to it as well. I mentioned podcasting, producing their own podcast. You might say, well, maybe I've listened to podcasts, but I have no idea about how I would have students create the podcasts. And that's what I said at first, too. On our campus, we have people that help us with that, get us started, give us great feedback. And any of you who are watching this who are college and the high school teachers, you have access to central faculty resources as well. So if anybody here is a college and high school teacher, and here I mean watching this, feel free to email me. It's on the very first slide at the beginning, and I can put you in contact with our campus people. But if you don't want to do that, or you're not affiliated with Central Washington University's college and high school program, this is a good resource right here. The New York Times actually has curriculum that you, the teacher, can use for teaching about it. So you can see here in this section, students analyze the elements and techniques of both podcasting and storytelling. So this guides you through teaching podcasting. We've got at least one other professor I know who uses this, an English professor. So the word storytelling here reminded me of that. She basically has the students tell their stories. They do some writing, of course, a lot of writing, but they also tell their stories through podcasting. And then Flipgrid as well, lots of resources that are built into that. This was the first website when I first flipped over to this, but this is PhET. A lot of you have probably heard of that. Interactive simulations started in physics. That's the PH stands for that, but they have lots of different. So if I just highlight this, you can see physics, chemistry, math, earth science, biology, and some of them are multidisciplinary. But I'm going to go back to the presentation here. And again, sorry, this is kind of clunky, so let's see if I can share this. Here we go. So this is the slide that we just saw. This slide has free physics and astronomy. I put labs in quotes because they're not necessarily all lab activities. But I highlight some different types, so it's not just this random list of things. So there are different ways for you to organize, or different types of tools for doing labs in an online environment. So the first one here, I call them field-based investigations. The third one there is a hot link just to some generic field work, how to do that in a remote environment. That's focused more on biology and earth science. And I haven't actually, I've read it over briefly, but I have not used that, but it was recommended by a good colleague, so who has used it a lot. But if you are teaching physics and astronomy, a couple of great field locations are the night sky or a toy chest. So balls, cars, they make great physics tools, flashlights, although that's probably not in a toy chest, great physics tools. Computer simulations, so I already showed you PhET. Some of the rest of those, O-Physics is another one that's good for physics. And AAP is the Nebraska Astronomy Applet Project. That has some great astronomy simulations. One slight downfall of that website and AAP is that, just this one right here, a lot of these simulations are flash-based. So there are a few components of that that are being converted to, and as you know, Flash is going by the wayside. So there are a few ways to access parts of this that are non-Flash based. Well, one is to use an old browser, but still some great resources here. Stellarium, web, that's a browser-based planetarium program. You can also download Stellarium. Worldwide Telescope is a browser-based and downloadable program. So remote instrumentation, controlling instruments from your computer. I use microobservatory when I teach introductory astronomy. Students control a small telescope. They can request images, and they do a little research project based on this. And I've got examples from all of these ideas on the next slide. You can use shared data. Like I said, there's a lot of data out there. My NASA data, that is, even though it's got the word NASA, most of this data is actually Earth-based. So there's a lot of weather and climate data here. And this is data that students can analyze. Some of it is just virtual spreadsheets worth of stuff that students can use and try to figure things out. The Vernier Sample Data Library, Vernier, they make science instrumentation for the high school and college level. They made some data that could be gathered from their instruments. So current data, motion data, and so on, that you would normally use the instrumentation in your class, but if your class is virtual, you can have students analyze this data. Even if you are meeting face-to-face, students could analyze this data as a pre-lab, and then they get to the classroom and actually do some of the work with physical equipment. Citizen science projects are another good way to get at science. So both Zooniverse and SciStarter have, and these aren't really experiments. These are, for the most part, what happens is scientists will put their work on Zooniverse or SciStarter, and citizens, so people, you and I, will look at this and try to analyze the data. So for example, Zooniverse, one of the Zooniverse projects is looking at the moon. Another one is looking at Mars, and looking at it, there are lots of high resolution images of the moon, high resolution images of Mars, and computers surprisingly aren't very good at telling the difference between something that's kind of fuzzy and something that is just a small crater. Or another one is looking at galaxies. Computer is not very good at telling the difference between just a fuzzy star and a galaxy, but humans are. So humans look at these pictures, and there's usually maybe an hour-long, 30-minute long practice session. And then after that practice session, humans will classify different pictures, and multiple people will get the same picture, so there's some cross-analysis. And if there's a picture that every human that looks at it says it's just a fuzzy patch, then that's going to be a low priority for the scientists. A picture that every human classifies as a galaxy, that's going to be a high priority picture for the scientist. But it's not just astronomy. Zooniverse, of course, has a lot of astronomy, but there are other things as well. So one of the projects is bird watching or butterfly watching. During the migratory time, people will go out and do a bird count, or they'll take pictures of plants in the area. So scientists can look at are certain plants blooming earlier as time goes by, or in different parts of the United States or the world compared to the year before and the year before that. So really, citizen science is for the most part science, well, it could be students, but people either gathering data for the scientists or doing a preliminary data analysis for the scientists. I mentioned that PhET has a lot of different resources. A couple more that I have not used very much. Teach the Earth has more Earth and life science resources, but there are also physical science resources. Vision Learning has a lot of resources for all of the sciences as well. It doesn't have quite as many lab activities or simulations as PhET, but it is another good resource. And one thing that I haven't mentioned at all, because I haven't used it, I have not used them very much, but there are apps on your phone that gather data. So your phone is a little computer. Your phone is a light sensor, a sound sensor, a motion sensor. And there are people who have used the capability of that to program. Well, I guess they haven't done the programming of the actual sensors, but how to take that sensor data and make it more usable for students. And I don't even mention that here. I haven't used that. That could be a source of a future video. So here are 5 online labs that I have used. So these are specific assignments that I've done in my classroom, both in online class, fully online class, and a class that's mostly face-to-face, but there's some online components. And I say these are yours to review because on the next slide, I'll just give you some prompts here as to how you could critically look at these and say, oh, I kind of like this idea, I don't like that idea. But I gave you something from each of those choices on the previous page. So the static charge is using household materials, sticky tape, and tabletop. Coulomb's law is using a simulation, but it's not just clicking buttons and looking at numbers on a screen. It's actually testing a hypothesis. So in Coulomb's law is related to electricity, and I probably should have an apostrophe there before the S. I apologize for that. Because Coulomb was the one that observed this empirically. But it has students making a hypothesis. So if we have 2-point charges, what do we think the relationship's going to be with the force or electric field? If we have a wire and a point charge, what's the electric field going to look like? This group lab simulation, and I'm actually going to show you a couple of these. We'll go off the slideshow and look at those briefly. But how do I set up a group simulation, a group lab activity? Ohm's law, that uses some of the Vernier data about circuits. The NAAP, Nebraska Astronomy Applet Project, one of their simulations is motions of the sun. So here's the activity I use for that. And then 2 projects. I mentioned the online telescope before, Micro Observatory. This will link you to my online observation project. And this link goes to something that in and of itself has links embedded in it. So you could take this project pretty much as is if you wanted to use it in an intro astronomy class. And then a recent addition to my, I guess, high-tech teaching, if you want to call it that, is having students make a celestial tour using Worldwide Telescope in online astronomy application, online sky application. So applying what you've learned, obviously you can stop this right now if you want. Perhaps you've stopped it 20 minutes ago, and if that's the case, you don't hear me saying these words. But you can review some of those assignments. If you do want to copy, or if you want to type on the assignment, try it out, download it, and or copy a version to your drive. So all of these are on Google Drive. If you have your own Google account, you can copy it to your drive, or if you don't, you can download it as a Word document or PDF or one of those open source word processing documents. And then you can access the resources, whatever they are, and then work through part of the assignment. And some of the questions that you should ask yourself: in what ways does this assignment engage students? If students were doing this in a fully online environment, is this engaging enough? If I meet with the students every so often, is it better that I sort of set this up with the students and then they do it on their own, or they do it on their own and then we talk about it? In what way does the assignment simulate a face-to-face lab or project? In what ways does it not? So how could the assignment be improved? And if there are some good aspects of each of these assignments, how could you apply some of those good aspects to other assignments? So for example, if you're a biology teacher, none of these assignments are biology related. Most of them are from circuits and electricity or astronomy. If you're not even if you're teaching physics, but you're not teaching much of those concepts, how can you use some of what is there to aid you in creating your own assignments? So I'm going to just share a couple assignments here with you. And again, you could be watching this on your phone, and if that's the case, this print is super duper tiny. But if you look at this, so I've got objectives, materials. This one is fairly prescriptive. And when we do this in the class, we also look at charged rods, so rubbing fur on acrylic and glass rods, or silk on acrylic and glass rods, and how do those things manifest themselves? Well, students at home aren't necessarily going to have that material, so I've got a link to a video that shows that. So that's another way to do things, and I guess that's sort of a subset of data that's publicly available. An online demonstration, a recording of a demonstration, really is publicly available data. So this, I guess, would be material that you'd find around the house, plus publicly available data down here. Here is one of the activities that uses a PhET simulation, but also is a group activity. So one of the ways I do that is I have students, so they gather some data, and then each student comes up with a trend line. And then they figure out, well, what is the average trend line for their group? And this just gets at the fact that any individual might have, if professional scientists have determined something is an R-squared relationship, and one person might get R to the 1.9 power, another person R to the 2.3 power, another person R to the 1.6 power. When you average those together, and actually, I forget what this one, electric potential and distance for a point charge. So yeah, I just arbitrarily said an R-squared relationship. So not all the examples here are R-squared relationships, but you average it out, and you're probably going to get a trend line power that is closer to what the professional scientists have come up with. And we do some qualitative stuff as well. So students have to make some different shapes here. So student 1 makes one shape and maps the equipotential, or the potential, electric potential. Student 2 makes another map. Student 3 makes another map. Student 4 makes another map. And then they copy and paste them, and then all the students make some judgments based on that. And by the way, for all of these, I have any group project, they do a group critique as well. They do a peer evaluation of how well the people in the group did in terms of the quality and quantity of their work. So I hope this was helpful to you. Go back, and actually this would be a good time for me to go back to the first slide. I probably should have done this before, but let me just get you one last time to look at the short URL. So go to tiny.cc / lowercase r, lowercase v, 27, t, and z. And those characters don't stand for anything. That was just randomly generated by that tiny URL company. Thank you for watching. And if you have any questions or any comments like, this was terrible, who pays you? keep that question to yourself. But any other questions, send me an email. And again, you can see that right there. Thanks. Bye-bye.